Hi, in this video, I want to talk some more about the sampling distribution for the importance sampling approach that we introduced in the previous video. So we saw we've got some potential here. I want to talk a little bit more about what potential we have for better performance, and then talk a little bit about how we might effectively choose that sampling distribution to make sure we get benefits rather than the problems out of doing this extra step, okay? So the whole strategy is really predicated on us getting a good sampling distribution. Let's talk about that a little bit in the following slides here. And the goal here is let's try to get more failed samples and not waste our time sampling a bunch of safe cases. And we'll just use that important sampling distribution to sort it out. So one option, because we won't belabor this one because we'll end up having an even better option, but we could take our problem, transform the whole thing to standard normal space, just like we have been for form. And then we could do our sampling of U's instead of the X's. But then we could also, we've got a little benefit here because we've got this radial symmetry, and we know that once we know U star, from say a form calculation, we know that there's no failure points within a radius of beta from the origin. So we could sample only outside of that sphere of radius beta, right? So our sampling points would be scattered in U space, and we wouldn't worry about like which direction to go, but we wouldn't have any samples inside the radius bit, okay? So when we transform ourselves to U space, then the true distribution would actually be the standard normal PDF. And then the sampling distribution would be some distribution where the PDF is equal to 0 if the norm of U is less than beta, all right? So we could take a standard normal PDF and just cut the hole out of the middle of it, or we could come up with some other distribution. So that would be one idea. And I bring that up just to say, we're trying to take advantage of knowledge about the limit state function. And if we do a form calculation and we know a distance away from the origin that the limit state function is with that beta metric, we could use that in coming up with the distribution. So that's an idea. Turns out, and there's occasions where that is a pretty good strategy. More frequently, we can also use our form results, but we could put our sampling distribution centered at the design point, okay? The idea here would be do a form calculation again, find that design point, and then I guess to illustrate this up, so if the gray lines are the original PDF contours, and then we find the design point X star, so we're back in X space now, then the dashed black lines would be our sampling distribution contours. And so this is what I drew in red a few slides ago. So we'll get lots of samples around the design point. And if we think that's the most likely place to cause failures, that's a good place to take lots of samples from. And we could benefit from that, right? And so at this point, if we're going to put all our eggs in the basket of this design point, or put them close to the design point, raises the question, so how can we justify that that's a good strategy, right? So if we go to the design point, I'll say approximately half of the sampled points are going to fall in the failure domain and half not. And it depends on how nonlinear the limit state function is and if it's concave or convex. But let's say if it's half, then I could get kind of 200 simulations and I'll get 100 failures out of those if in the important sampled domain. But if it's a regular Monte Carlo, it's going to take me about 100 divided by PF simulations to get 100 failures, right? So if the probability of failure is 1 in 50, then it's going to take me kind of 50 times 100 in order to get 100 simulations on average that caused a failure. And that's where we were running into these tens of thousands, hundreds of thousands, maybe millions of simulations. If I'm thinking about kind of tens of thousands of simulations versus 200 simulations, I know I'm getting a big payoff there in terms of my computer time. This isn't a totally fair comparison because those 100 realizations from important sampling, those are no longer Bernoulli trials where I've got my variance calculation from before. I now have kind of these failures weighted by an important sampling weight, and those important sampling weights vary also. That introduces some variance. So 100 important sampled failures are not quite as good as 100 crude Monte Carlo failures, but 200 simulations versus tens of thousands of simulations is pretty compelling. And even if I've got to do some thousands of simulations with important sampling, this is pretty interesting. Okay? So that's one benefit. If we can get ourselves to the design point, then we're in good shape. And just with a general Monte Carlo problem, that might be a little hard, but because we've already developed these, say, the form algorithm to find the design point, we can use that form calculation to inform a good sampling distribution and then make sure that this Monte Carlo simulation is going to work well with this importance sampling framework. So the pair of our analytical solution to get a design point plus this importance sampling is really a nice strategy. There's another benefit of importance sampling beyond just reducing the number of simulations, is that as long as I'm choosing the distribution that I'm sampling from, the K of X, I might as well choose something that's convenient as well as something that works well numerically. And with this strategy, I could say, I'm going to sample an X1 and an X2 from this K of X distribution that is, it has independent components, right? Versus the original distribution had some dependent. And visually, I'm drawing that conclusion by looking at the kind of the angle of the joint PDF. So because that gray PDF has values that are occurring on an angle, that means that large X1s tend to occur with large X2s, right? There's a dependence. Whereas the dashed black line PDF, that's got it's ellipses and their principal axes are in the X1 and X2 directions, giving an indication that the value of X1 is not dependent on the value of X2. And so for Monte Carlo simulation, that's convenient. Then I can just sample my X1s, I can sample my X2s and put them together, and I don't have to worry about that dependence. And then the dependence is still in the problem, like my probability of failure is still going to account for that, but it's going to account for it in the importance sampling way, right? So the K of X, I'll sample from an independent distribution, but then when I go to my importance sampling weight, let's go back up where we had the formulation for this importance sampling weight. The denominator is an independent distribution for the components of X, but the numerator is dependent. And so this ratio here is going to account for the relative likelihood of the sampled values that I produced. Okay. So that's got a nice practical benefit as well. If I don't feel like simulating dependent random variables, I can just do some importance sampling to get around that. Okay. So we're honing in on a pretty nice strategy here. And so some thoughts about what we should be thinking about when we're picking a strategy here. There's a few considerations. So one is that sampling distribution must not be zero anywhere interesting. And specifically, the interesting part is in the failure domain and where the true distribution, f of X, is non-zero. So I may need to make sure that I'm sampling from all the interesting places. So if I've got a sampling distribution has a zero PDF, I'm never going to generate samples there. And I could get myself in trouble. And let's go look at a picture here maybe. So we'll just pick this picture to have something to look at. If I picked a sampling distribution that was like here, let's say, just to really push the limit. So let's just say K of X is uniform in this box. Okay. So that would be a bad choice, right? So I'd sample a bunch of points in here and I wouldn't sample anywhere else. And anything in there is equally likely, just keep it simple for purposes of discussion. I'd never sample anywhere else, right? So I would get a zero probability of failure. And that wouldn't be the correct answer though. And the issue is if I go find one of these, this formula here, I'm generating samples of these xj's from distribution. Let's see, we pick this middle line, right? So this PDF here is zero in kind of important places where there would have been failures, right? The whole failure domain have a zero PDF here. And this equation still looks right, but the problem is I'm dividing by zero in the denominator down here. So that's a problem, right? Now the K of X can be zero, and I can divide by zero if this indicator function is zero. So in places that are safe, that's okay, because this was going to be a zero, and so it doesn't matter what the value of this importance sampling ratio is. K of X can also be zero wherever the true PDF is zero. So if the true distribution doesn't have negative values of X, it's also fine that my sampling distribution doesn't have negative values of X, that it has zero PDF there. But if the true PDF is non-zero and the indicator function is non-zero, but my sampling distribution has a zero, then the zero in the denominator here plays a role, and it's going to eliminate areas of the X distribution where I would have had failures, and I'm going to underestimate this probability of failure. Okay. And so that's the problem I have to keep an eye on. And the bad thing is if I'm just naive and I do this blue sampling distribution, I'm not going to know that I made an error. I never get a divide by zero error because I'm not evaluating that integral, right? I'm just taking all these observations and I'm saying how many caused a failure. And so I don't get a diagnostic indicating that I made an error. There's this kind of secret mistake floating around in there and I get the wrong answer. So we have to be careful about that. But choosing a good sampling distribution, we can get around that. I'm going to take this off just to avoid confusing that figure. Okay, so let's talk some more about that. So that's an important thing. So beyond just being non-zero, we want to choose the distribution well. And so what we would like to do is we'd like to sample as little as possible in the safe domain because those values are a waste, right? I'm going to sample them and then I'm just going to multiply them by a zero in that indicator function and throw them out, while not violating the above condition. It's this condition up here. So and there's a little bit of a tension here, right? So sample as little as possible means like try to make the sampling distribution PDF equals zero some places, but I don't want to make it zero anywhere interesting. And I don't necessarily know where interesting is before I start this, right? That's why this idea of sampling at the design point works pretty well. I'm still sampling in the safe domain, but I'm not sampling, I'm not sampling a vast majority in the safe domain. Okay. And then a note in terms of this kind of using the design point, which helps us with the above two items. We may not get a unique design point sometimes in some system reliability problems and things, but we'll return to that later. I may not even need the third bullet point right now because we're not quite ready for it. Okay, so with that in mind, here's a kind of a practical approach. We started heading towards this. We can start off by doing form, or if we want, we can actually just do a second moment method to find this design point x star, right? So we're trying to find the point on the limit state surface where we have kind of high probabilities out of our true distribution f of x. The second moment methods actually would work effectively here as well, in that there's nothing magic about this design point in terms of my Monte Carlo sampling, because I'm going to go take a bunch of samples anyways, and I'm not going to just calculate at a single design point. And so if a second moment method gets me close to the form design point, probably comparably good, and second moment calculations may be easier than doing form. I might have to not worry about my transformations as carefully. But one way or the other, with one of the techniques we've developed, let's find a design point. And then let's get a sampling distribution that's centered on that design point. So that'll put my plot for my samples in the interesting part of the problem. And then we'll get important sampling will give us an updated PF estimate. If we had gotten the probability of failure from form, we could get a new result from this important sampling. And then we could compare the two to say, I think form gave me a good place to do my important sampling. I think I'm doing a good job there. Does my important sampling probability of failure, is it bigger or smaller than my form answer? Or is it basically the same? And that'll tell me a little bit about the form approximations I made. And so the two of them working together work really nicely in that regard. So that's one good strategy. And there's no unique sampling distribution approach that we have to use. But as long as we've got those insights from our other reliability calculations, they're a nice starting point for doing this important sampling. And so this is a way to think about important sampling distributions. Okay, so that's our thoughts on choosing a good distribution for importance.